Welcome back to Logic, Language and Information. In today's lesson, we will formally define models of predicate logic, making precise what we mean by an interpretation of names and predicates. Keep in mind that a model for predicate logic is analogous to one row of a truth table in propositional logic. In each case, they contain all the information required to determine the truth value of atomic formulas of the language. A model for predicate logic consists of two parts: a non-empty domain D of objects, together with an interpretation function which interprets each name and each predicate in the language using objects in the domain D. We will write a model M as a pair D, I to indicate these two parts. This lesson will focus on the interpretation part with lots of examples. Let's begin with a model containing three objects, namely three scientists: the 19th century English mathematician Ada Lovelace, the Austrian-Czech logician Kurt Gödel, and the German-born physicist Albert Einstein. Now, suppose our language includes two names, A and B. One possible interpretation is to interpret the name A as Ada Lovelace and the name B as Kurt Gödel. A for Ada, obviously, and B for, well, Brno, the birthplace of Kurt Gödel. In 1906, when Gödel was born, Brno was part of the Austro-Hungarian Empire, but today it is in the Czech Republic. That is one possible interpretation, but there are several others. We could keep A as naming Ada Lovelace, but instead interpret B as Albert Einstein, say because the third letter of Albert is B. But there are clearly more possibilities, and we really don't need to give any explanation for a particular interpretation. A and B are just symbols functioning as names, and they have to be mapped to some objects in the domain. We could interpret A as Gödel and B as Einstein, or have A and B as two different names, both denoting Gödel, or both denoting Lovelace, and so on. The only requirement on an interpretation I is that each name in the language must be mapped to an object in the domain. If A is a name, then I of A is an object in the domain. In our size 3 domain, consisting of Lovelace, Gödel and Einstein, how many different ways are there to assign objects to two names A and B? You might want to map out the possibilities before making your choice. How did you go? The correct answer is 9, which is choice E. With 3 objects in the domain and 2 names, the total number of ways to interpret those names is 3 to the power 2, or 3 times 3, which is 9. In general, in a finite domain with n objects, if there are m many names in the language, then there are n to the power m different interpretations assigning objects to names. Now let's turn to interpreting predicates. Let capital F be a one-place predicate symbol. If we interpret F to mean is a mathematician, then I of F will assign 1 or true to Lovelace and Gödel and 0 or false to the physicist Einstein. Suppose instead that the predicate symbol F is interpreted to mean died before the end of the 19th century. Then I of F would assign 1 to Lovelace and 0 to both Gödel and Einstein. Yet another interpretation, say the predicate symbol F means has their birth date in the first half of the month. Then I of F would assign 1 to Lovelace and Einstein, their birth dates are 10th of December and 14th of March respectively, while I of F would assign 0 to Gödel, whose birth date is the 28th of April. So, staying with our domain consisting of Lovelace, Gödel and Einstein, let F be a one-place predicate symbol, interpreted as meaning is a physicist. In this case, I of F would assign 1 to Einstein and 0 to both Lovelace and Gödel, since they were mathematicians. So I of F divides the domain into two camps. One with all the objects assigned 1 because they do have the property denoted by F, and the other with all the objects assigned 0 because they do not have the property denoted by F. Equivalently, for a one-place predicate, we can use a one-dimensional table with a column of 0, 1 truth values, with the length of the column equal to the size of the domain. So for a size 3 domain, as we have here, we need a length 3 column of truth values to represent I of F. Thinking of an interpretation I of F as a one-dimensional column of truth values, and staying with our size 3 domain consisting of Lovelace, Gödel and Einstein, how many different ways are there to interpret a one-place predicate symbol F? Consider your choices. How did you go? The correct answer is 8, which is choice D. There are 8 equals 2 to the power 3 many ways of filling out a length 3 column of zeros and ones. As usual, if you have any comments or questions, go first to the course notes and then to the discussion boards, and I'll check in on the discussion there. In general, in a finite domain with n objects, there are 2 to the power n many different interpretations of a one-place predicate symbol. Now, consider a two-place predicate symbol R, and suppose we interpret RAB to mean that A admires B. So the first admires the second. Staying with our now favourite domain consisting of Lovelace, Gödel and Einstein, the intended interpretation I of R would have Lovelace admiring, say, Lovelace, but not admiring either Gödel or Einstein because Lovelace was dead before either of them were born. I of R could have Gödel admiring Lovelace and Einstein, but not himself. Gödel was plagued by anxieties. And Einstein admires everyone, Lovelace, Gödel and himself. Here we can use a two-dimensional table and we look at the intersection of rows and columns to check, for example, whether Lovelace admires Gödel. We look at the intersection of the Lovelace row with the Gödel column and we see that the entry is 0, so no. To check whether Gödel admires Lovelace, we look at the intersection of the Gödel row with the Lovelace column and see that the entry is 1, or yes. For a three-place predicate symbol, each interpretation must assign a truth value to a 3-tuple or ordered triple of objects in the domain. In general, each k-place predicate is interpreted by an assignment of truth values to all ordered k-tuples of objects in the domain. 3-place and higher k-place predicate interpretations are more difficult to represent using a table, so some other listing or description is usually required. Remember that a predicate behaves like a proposition with holes in it. If we fill in the appropriate number of holes with names for objects, then the result is a proposition that is either true or false. This brings us to the end of this lesson formally defining interpretations within models. In the next lesson, we'll get to the heart of predicate semantics and see how models determine the truth or falsity of predicate logic formulas. So see you then.